So let's build this little ultrasonic levitator. I was browsing eBay the other day and came across this thing, and for $7 I was more than willing to take a chance here. So if we look at the eBay page, there's not an awful lot of information. Nobody really takes credit for making this thing. X Module X is the name of the vendor here. We've got a partial schematic and a little bit of instructions maybe, and a picture here. There's not an awful lot more detail further down. But sure enough, if I do a web search on exactly this term with instructions afterwards, I end up with a couple of interesting hits here. And this first PDF that shows up does indeed look exactly like this board. So I'm going to use this as my guideline here. And again, nobody takes credit for this silly thing. I wonder how these designs just materialize out of nowhere. And then there's also a hit on Instructables. So it's not exactly the same kit, but a similar idea. Looks like almost exactly the same standoffs. And if we look at what's in the bag here, so it's not packaged terribly well, but that's to be expected for $7. So let's see what we get in the bag here. This is not instructions, it's just a packing list in partial English and partial Chinese. And in here we've got the two ultrasonic transducers, we've got the 3 circuit boards, including the one we need to solder up mostly, some styrofoam beads. I will have to have one of my coworkers translate this for me. I have no idea what that says. A bunch of standoffs here, and what's interesting is we've got a couple of ICs that are in their packaging, and then another IC just sort of loosely floating around here. So hopefully that doesn't cause any problems. Oh, the other thing I'm going to try and do here is I'm way overdue for a new microscope, but I had this old monoprice microscope kicking around, so I am going to see if I can actually do some SMD assembly with this thing. Looks like the smallest component size here is 0805, which I can do comfortably under a microscope, under a real microscope, so let's see how we do with this thing here. Okay, so we're going to start the assembly process here. And I'm probably going to speed over most of this here. So the first thing we'll do is install our transducers. And let's double check that we got that right. Yep. So the metal can solders into the ground plane. Sort of see what's going on here. The power to the transducers actually conducts through these standoffs here. We've got the copper trace going into the center here, and it's on both sides here. So when we bolt these together, both of the transducers get the same signal. Kind of wanted to get that done just to have something pretty to look at, even though this is out of order based on the instructions there. Okay, so let's get soldering. Okay, so here's our setup, and what I'm noticing is this camera is surprisingly sharp, a little bit laggy, so that's probably going to be the biggest deal here. I think the first IC that we'll install is this guy here, and so I'm just going to have at it here, and I'll probably speed up this process so I won't be narrating. Alrighty, my friends, that was excruciating. This thing here, going in the trash. Yeah, so need to treat myself to a new microscope in the not too distant future. So let's finish off the last of the assembly here. If I can figure out where these guys go. Yeah, so this goes here. oh gosh, look, it's idiot proof. You can install this any old which way. Yeah, so all of these traces are driven, even though there's only 2 that are going upstairs. Okay. Okay, check that out. That didn't take too long. Yeah, so I guess, boy, what do we have to do? Oh, I know. Fire this thing up. All right, let's try to float some beads in this thing. So I've got the, I've got it clamped in my favorite little Hacko vise here. And what I'm going to do is I actually took a little piece of screen from the front of another ultrasonic sensor and made a little cup out of it. And we're going to take some of these little beads, see if we can't float them. Right, so, and I got this trick from the Action Lab. Look at that. See a little floating bead? Okay, let's see if we can get another. And another little node there. Do it. Usually we can get one in the center. Oh, there it is. So we've got 2 little floating beads. How cool is that? And I think that's probably about all we're going to get. But I'm going to take a small one here. See if we can float that. Oh boy. Okay, so the small one here, you can't really see it. It's floating. It is stuck at the top. And let's see if we can knock. Let's see if we've got all of the nodes represented. Oh, look at that. Wow. See how close those are together? Okay, now this is a challenge. Let's see if we can't get one more. Oh, look at that. We've got 4 of these guys. Okay, hang on. I cannot believe this is working. Oh, wow. 1, 2, 3, 4. Okay, we can get another. I can sense it. One more. Can we get one more to float? Oh, that's a big one. Let's get a smaller one. Come on. Oh, yeah, I don't think that counts as floating. So let me see if I can give it a little hand. Oh, that's a larger one. Let's get a smaller one. That doesn't count. Okay. I think that's about as good as we're going to get. Okay, so we have got, let me see if I can scoot this guy down a little bit. And in. Yeah, so we have got, that doesn't count. We're not going to count that one. We've got 4 little floating styrofoam beads. There's actually a 5th one stuck up top there. So we've got 5 beads. Oh, one fell out here. Yeah, but see, you get the idea here. Now, this is all well and good, but let's take some measurements of this thing here. So remember, these ultrasonic transducers can act both as transmitters and as receivers. And I happen to have here a whole bunch of ultrasonic transducers that I had for another experiment. So let's see if we can use one as a microphone. Okay, great. So what I'm going to do here is I'm going to take my AD-ALM 2000 and I'm just going to use it as a basic oscilloscope first here. So I'm going to take channel 1 and the inputs to this thing, the sensors here actually put out quite a high signal level. So I'm just going to aim this and look in the scope screen here, right? We've got quite a high signal level. Okay, this is 1 volt per division. And you see, I'm getting like a volt worth of signal here. Okay, how cool is that? And then furthermore, let's take a little cone here. This is snipped off of a silicone adhesive nozzle, and it's just the right size to do sort of a press fit here. And let's see if we can get a sense of where the intensity is greatest. So I can move this up and down, and I can actually I don't think I'm fooling myself. I think we're really looking at the nodes and antinodes. Okay, so if I can sort of sniff up and down, and I can see the standing wave pattern with this little ultrasonic transducer here. Okay, you know, I think we need to geek out a little bit. Let's see if we can see the phase difference. Let's take a measurement of the electrical signal that's being driven into this thing and put it on the other channel. Okay, so here what I've done is I've taken some breadboard wires and sacrificed them to tap into the electrical signals that are driving the transducers here. And I've hooked that up to channel 2 on the AD-ALM 2000. Okay, so it seems I had a bit of an issue with Scopy crashing on Windows here. So I'm actually VNCing into a Raspberry Pi here. And that's a little hint. We're going to need a Raspberry Pi anyway, so why not do it now? So as you can see, I've got channel 2 of the M2K connected to the drive signals to this transducer. So that gives me a nice reference square wave here. And look at the drive level of this thing. This is 5 volts per division, and I've got 2.5 divisions here. So yeah, over 10 volts worth of drive. Yeah, and I'm supplying 12 volts total to the board. So yeah, plus minus 24 volt drive to those sensors here. So let's take our little probe and move it up and down the column and see what we get. And you know, this is always more satisfying when we have a styrofoam bead floating in there. So let's get a little guy floating. Thank you, Action Labs, for that little hint with the tiny screen there. Okay, so what we're doing, okay, so things we're going to notice here is here I've got here I'm in an antinode, and I've got my drive signal in phase. And I'm going to go down. Oops. In a node, you notice I've got a phase shift of about, oh no, there's another one. So there, I've got out of phase, and then here's a null. All right, you know, the thought occurred to me to motorize this thing to get a little linear actuator, but that is for another day. Okay, all right, so we're probing along the line here, and yeah, so we're not done geeking out yet, because here at Thorne Scientific, we don't just believe in having the bare minimum amount of flare here. Wouldn't it be cool if we could actually hear what was going on? Alrighty, so now we're going to take a little trip to the extreme nerdiness here. So I mentioned before that we're running a Raspberry Pi, and the reason is I can run ADI Kuiper Linux, which comes with a program called GNURadio Companion pre-installed. So GNURadio Companion is intended for software-defined radio applications, but we can, you know, it's a general-purpose signal processing package here. So we'll get to that in a minute, but I've got a Raspberry Pi, and it is connected to my AD-ALM 2000. Remember, I was just running Scopy on the Raspberry Pi, talking to the M2K here. I've got the Levitator here, and also on the Raspberry Pi, I've got a little USB sound card. So this is a cheapy sound card from Adafruit that was chosen because it's compatible with Raspberry Pi, no drivers or anything like that installed, and that is output to a microsonic speaker amplifier. This is an artifact from the 1980s, and I'm going to switch over to the camera microphone in a minute, but first let's look at this GNURadio flowgraph. Okay, so here we are in GNURadio, and if you've never seen this before, it's a simple sort of a block. it's a flow graph way of implementing signal processing chains. So there's all kinds of really interesting blocks in here, all sorts of things for modulation, demodulation, frequency translation, filtering, etc. here. And it just so happens that I can take data from a number of sources here. So it supports a number of software-defined radios. It supports the AD-ALM Pluto, and there's a block for the M2K, or AD-ALM 2000. And so what I've got here is I'm taking channel 1 from the M2K into the flow graph. I've got a sampling frequency of 100 kilosamples per second, and I want to look at the raw data itself here, just as a point of interest. And then the first thing I do with that data is I send it through a high-pass filter. So I'm not interested in the DC content of the signal, so I strip that out. The next thing I do is I send it into a complex quadrature demodulator, and I've sort of built that out manually from blocks here. And conceptually, it's pretty simple. I take a signal source, a complex sinusoid, at a sample rate of 100 kilohertz, but with a frequency that I can adjust either above or below the 40 kilohertz drive signal of the Levitator. And I've actually got that adjustable with a little slider, and you can see that I default to 39 kilohertz, so about 1 kilohertz away. So I take that complex sinusoid and I split it into real and imaginary components. Then I multiply that with the incoming signal. Then I add them back together, and then I'm at a sample rate of 100 kilosamples per second at this point, and I need to get that sample rate to something that a typical sound card is capable of receiving. So a sound card will have a number of standard sample rates, 22 kilosamples per second, 48 kilosamples per second. And so I've chosen 48 kilosamples per second. And the way I translate those data rates is with a block called the rational resampler. So at this point, I've resampled the data to 48 kilosamples per second. We send it to a plot so that we can see what's going on. And then it turns out you don't want to overrange your sound card. So I've got a little volume control here as well. So let's cross our fingers and let's see if this works. Okay, there it is. So let's turn this up, and we may not be able to hear it yet. Okay, so I'm going to take a pause here for a second and switch to the camera microphone. All right, we're up and running with our translator. And sure enough, how cool is that? So let's see if I can detect my nodes and antinodes. How cool is that? Okay, and we also have the ability to change our intermediate frequency. So let's do that. I've got a slider bar set up. Let's take our volume down a little bit. That is grippy. And let's look at one last little thing. So the frequency of oscillation is controlled by a little microcontroller on the bottom board here. And I've got the data sheet for that up. Yeah, so here is the data sheet for this microcontroller. And it's using an internal oscillator. So it's not controlled by a crystal or anything, which means it's probably sensitive to temperature. So let's hit it with a little freezy spray and see what happens. There we go. And then as that warms back up, comes back to life. Okay, let's turn this off. I don't know about you. I thought that was pretty satisfying. And this opens up possibilities for all kinds of interesting experiments. You know, you can go out and buy a bat detector for listening to bats as they're flying around using their echolocation and just exploring the world of ultrasonics that you couldn't normally hear. Okay, I think that just about wraps up this one, and yeah, we'll see you next time. Oh, and I will post the GNU Radio flow graph up to GitHub and leave a link in the description.